In this video tutorial, I'll look at steady-state thermal analysis of a thick cylinder, followed by static structural analysis using the temperature data from the steady-state thermal analysis. So we'll start by developing our geometry as before, and I'll use the same example as my previous transient analysis. So changing the analysis type to 2 dimensions and then starting the geometry using design modeler. It will be an axisymmetric model on the XY plane, so it has to be done on the positive x-axis. All I need is a simple rectangle, so creating the rectangle, just zooming in to get relatively straightforward structure here. So this is a basic rectangle, and I need to add my dimensions to it. So I know that the thickness of this was 50, and also the internal radius was 200, and the height of this we arbitrarily made that 200 as well. So let's change that in terms of meters. The thickness, let's change that to 50 or 0.05 meters. The internal radius, which is h2, that is 0.2 meters, and v3, that is 0.2 meters as well. So if we fit this view in, that's our basic rectangle that we are going to create a concept of a surface from sketch. So selecting the sketch, apply, and then that can then be generated to give us our surface, which is one part and one body. In Workbench project schematic, let's start the mechanical model. The design modeler geometry is now attached to our mechanical model. Our geometry is a surface body, and we need to change that 2D behavior to axisymmetric, and our material is defined already as structural steel, and this has got the typical properties as well as structural as well as the thermal properties. So the other thing we need to do is mesh this surface. So let's create our straightforward sizing on this surface. We'll need to define an element size. In terms of meters, it is 0.005, that's 5 millimeters. So if we click on mesh and then generate, that creates around 10 elements through the thickness of this thick cylinder. So remember, this is an axisymmetric model, and we are doing a steady-state thermal analysis. Initial temperature we can always define similar to our problem definition as 20. Analysis setting, there is only one load step in this one because it's a steady analysis. We need to define our convections. Convection on the inside face, we had a film coefficient of 3000, and the ambient temperature on the inside face was 100 degrees, and we need to do the similar thing for the outside face as well. if we click on convection and then select outside line, that represents the outside surface. So one edge selected, film coefficient in this case was 50, and ambient temperature is 20. Let's say it's almost like boiling fluid inside the pipe and air on the outside surface. So that's the boundary conditions for steady state. And as I mentioned before, if you don't apply any boundary conditions at these top and bottom lines, that represents adiabatic boundary conditions, so no heat transferred from these surfaces. All the heat will go from the inside face to the outside face, like so. In the solution, we want a thermal result like temperature and total heat flux. And we can also look at our probe for the reaction to measure how much heat has been transferred. So I think this is ready to solve, and we can click on solve. And solution is done. In the results, we can look at the temperatures and total heat flux and the reaction probe. So the reaction probe is showing 1177 watts being transferred from inside face to the body. So that is similar to the transient analysis we've done before when it has reached the steady state. So in terms of the temperatures, it needs to be scoped to the surface. So let's generate the temperature again, temperature, and scope to all bodies, and then let's do generate on that one, or evaluate all results. So that shows us the temperature as a contour plot on the whole surface. The first temperature result was scoped on the bottom line just because it was scoped to that. Now the inside face is 98 degrees and the outside face is 94 degrees. So there's a small thermal gradient from inside to the outside, and this will result in relatively higher thermal expansion on the inside face compared to the outside face. The whole cylinder will be expanding in the y direction and also in the x direction, which is the radius direction. So because there's a thermal gradient, that results in differential expansion and also leading to thermal stresses. So the next part of this simulation will be looking at the analysis of these thermal stresses. If we go back to our project schematic, we can see that our steady state thermal analysis has got all these check marks ticked, all the results are available. Now what we want to do is use these results to do our static structural analysis. So move the static structural and drop it onto solution, and what that will do is it will create a new static structural analysis, but the engineering data, geometry, and model are all linked into the steady state thermal, and also the solution data is linked into the setup of the static structural. So if we right click and then do edit again on that, we can see that the model, geometry, materials, etc. is here, mesh is here, steady state thermal analysis is here, as well as the temperatures, etc. that we have just measured. Now we want to use these temperatures in our static structural analysis, and that appears as imported load. So imported body temperature. If we did an import load on this one, it actually reads the data from the previous analysis, and that will now be used as imported body temperatures to show our static structural stresses. So as well as this imported body temperature, we also need to specify our boundary conditions for the static analysis. So one of them, for example, will be to make this line fixed in the y-axis, so in the actual direction of the cylinder. Now we can do that under static structural and then supports, and this will be probably better represented as a frictionless support. So if we click frictionless, this line will be able to move in the x direction. All the nodes on this line will be moving in the x direction freely, but they are restrained moving in the y direction. So we are not applying any internal pressures on this one yet. We can do a solution based on that, and we'll need a total deformation and equivalent stresses, and we can also look at other stresses like the maximum principal, middle principal, minimum principal, etc. So if we run this static structural now, if we click on solve, what we can see is that this is minimum principal stress. If you look at deformation and then animate the deformation, we can see that the body, this is an axisymmetric body, remember, is expanding in the radial direction as well as in the actual direction of the cylinder. And this is the total deformation, so the maximum deformation is appearing as a magnitude the highest at the top right corner. If you look at the equivalent stresses, you can see that it's a relatively small stress, about 6 megapascals, and on the inside face, and also showing as high on this corner at the top. So if you look at maximum principal on the inside face, this is looking like a small compressive load or stress, and the outside face, it's a small tensile, and that's the middle principal stress, and that's the minimum principal stress. Now the interesting one is the equivalent stress, and 6 megapascals is quite small compared to the yield strength of the steel material that we are dealing with. Now we left the top face free to expand in the y-axis. There are a couple of different boundary conditions that we can apply in this one, and that will depend on what your real structure's support is like. Let's try, for example, fixing that fully, and then we'll also try coupling that in the y-axis. So another thing we can do here is, let's say, the total deformation, and we can increase the scale of the deformation. Let's say this is 5 times automatic scale. You can see how it's moving, and effectively you can see that there's a slight curvature because the inside face is expanding more than the outside face, so there's a small curvature being applied, and there's also significant movement in the y-axis. So these are exaggerated quite significantly, like 230 times the original displacement. The actual displacement is 288 microns at the maximum point, so a fraction of a millimeter. So let's stop the animation, and if we go back to static structural, we can add another boundary condition. We can apply a displacement at the top face, like fixing it completely in the y direction. So let's apply to that, and then solve again and see what that does to our stresses in the body. So that's completed okay, and what we can see here is when we animate this, that there's no expansion now in the y-axis. So the cylinder is restrained in expansion in its axial direction, but it is still free to expand radially in the x-axis. And if you look at equivalent stresses, now these stresses are very high. It's created a highly compressive stress on the inside surface especially. We'll need to see that if you click on minimum principal stress. You can see that the value of that is about 173 megapascals, and middle principal and maximum principal are shown here. The important one here is that because we have restrained this in the y-axis, the cylinder isn't free to expand in y, and that creates a highly compressive stress state, and that's evident when you print or plot the minimal principal stress. The other thing we can do is, well, let this free in the y-axis, but in the sort of equal amount on the top line. So we can look at our displacement boundary condition and right click and then suppress that, and we can then add another boundary condition. So that will be a coupling, and that's shown under conditions. So the first one is coupling, and if I select the top line, what I can ask ANSYS to do is to couple the nodes on that line in a particular degree of freedom. In this case, the y component. So all the nodes on that line are going to be moving the equal amount in the y-axis. So rather than displacement, I'm coupling it, and that means the cylinder is going to be free to expand axially as well as radially. But this is similar to that cross section remaining plane. So if we run this analysis, let's look at how much stress that will create. If we look at total deformation, we can see that the body is now free to expand in the radial as well as the axial direction, and the maximum displacement is still a fraction of a millimeter. The equivalent stress, the maximum value, is now almost like the first case, but you can see that the stresses are a lot more uniform through the thickness, through the length of the cylinder. So maximum principal stress is on the outside face, and middle principal stress, and that's the minimum principal stress. So essentially the inside face is expanding more than the outside face, and that's creating a compressive stress on the inside of this thick cylinder. So this is a quick analysis of a thick cylinder, first starting with a steady state thermal analysis and then moving to static structural analysis and then creating a thermal stress analysis of this. What we can next do is add a pressure load onto this. So in the analysis settings, we had one number of steps defined. We can keep that. We can define a pressure at the same load step. So let's do a pressure load, and then on the inside face apply, let's say, 100 megapascals magnitude. So that's going to be megapascals, so I need to go back and change my units just to make it more convenient to apply. So millimeters, kilogram, newtons, etc. unit system. So that's 100 megapascals applied. So that will again be a single load step, a static structural analysis, but this time it's going to have a pressure load as well as a thermal load. So the solution is done again, and we can see how the structure is deforming, and that's the total deformation. And we can look at the equivalent stress, which is the highest on the inside. Maximum principal stress, that will be similar to the hoop stress because the pressure is dominant in this case, pressure load. And middle principal stress, and that's the minimum principal stress. Minimum principal stress will be the radial stress, because again the pressure is dominant in this case. So if we click on equivalent stress and then do an animation, we can see that there is thermal expansion as well as pressure load applied in this particular analysis. So this concludes the thermal analysis, followed by a static structural analysis of a thick cylinder.